the business is to introduce Dr. Iain Neill from Glasgow University on collision magmatism to geothermal future in the Northern Highlands. So Iain is a lecturer, as said, in Glasgow University. He's probably going to tell us a lot more about himself than I can tell you. He's also on the editorial board of the Scottish Journal of Geology, so the report that's in your proceedings is written by Iain, and he's also been co-opted onto the council, of the Society Council, as a representative of the Scottish Journal, and as an expert geologist as well. So I'll just hand it over from collision magmatism to a geothermal future in the Northern Highlands. Thank you.
Okay, now I'm told this microphone and this one do not like each other, so
I've turned it off.
Hopefully everybody can hear. All good?
Can everybody hear Iain's voice?
Hello? Yes. Good. Okay. Very much. Thank you. So I want to say thank you. In particular, I want to thank the Geological Society here, both for letting me infiltrate the board, but also for funding that has helped in no small way with some of the data that goes into tonight's talk. And I also want to make a particular point of thanking some very enterprising communities in the Highlands of Scotland, enterprise groups, community councils and so on, who, with no geological background, have been willing to listen to me wax lyrical about the wonders of geothermal. And that's what we'll finish with tonight when we're finished with granites. So, use this one. Okay. My plan is really to tell you about some of the rather unusual things that we can get in what may appear superficially to be a very boring looking rock. We are surrounded by granites. There are over 100 substantive bodies of granite in Scotland. What can we get from them and why? We don't really understand them as well as we should. And one of the themes of that is how Scottish geological research, and indeed geological research in the UK, for a large part of the 90s and 2000s, has perhaps forgotten to research the UK. We go to the best place in the world to study a process, but we forget about our backyard. And now, with the energy transition, with pressure on geological resources, with an increasing awareness of the isolation of the United Kingdom from Europe, more focus has been put on geological resources that we have in the UK. The British Geological Survey have been instructed to pay more attention to what we have beneath our feet and what we can do with it. And this is filtering down to funding applications. This is good news that we want to understand more about the geology of the UK, both from an applied point of view, but also to go back to perhaps even historic problems that maybe you could argue should be long ago. I'm going to show you some new data about dating granites and how it's not all about just the date. And I want to show you that maybe we could improve on understanding how the tectonic blocks of the British Isles came together over geological time, but then become a little bit more political and ask ourselves, what can we do with the rocks that we have? And that's where the geothermal connection will come in. So let's go straight to it. Who am I? Standing in front of you. Well, I've been in Glasgow for 11 years. I should probably have been here before, but never mind, here now. I'm a Highlander. I grew up in Dingwall in East of Ross. Moved to St Andrews for my undergraduate education, PhD in Cardiff, and the postdoc in Durham, which were entirely blue skies. Problems of plate tectonic evolution, problems of magmatism in far-flung places, nothing applied and nothing Scottish. I think perhaps as I get older, I realise more about where I grew up, and I realise more that the reason I started geology in the first place is because the future of where I grew up is important to me, and I believe quite fervently that if we knew more about the geology in certain ways, maybe we could make use of it for good. And you will hear a lot in the news about the race to net zero, the energy transition, the justness of that transition, debates about wind farms across the Highlands, but energy bills going through the roof. Maybe we geologists have a role to help you in some way. We'll outline that as we get to the end of the talk. And ultimately, I feel that's where I'm going in my own research interests. I will do anything from the completely blue skies, why is there a volcano here in Armenia, let's say, through to what can we do in the Highlands. So, why granite? What is it about granite? I'm not going to show lots of pretty pictures of different granites and granitoids and granodiorites and tonalites and all of the array of grey and pink things that you see in the field. But to me, granite body, to be a little bit philosophical, granite body is the ultimate end point of an igneous system, particularly in continental settings, particularly in continental arcs, in collision zones. Granitic magmas have this ability to take with them a record that is unparalleled in terms of understanding processes of melting, crustal evolution, all those potential.
Can you just ask people to mute? Everyone's on mute. Everyone. Okay.
Okay, thank you. Ultimately, I kind of like a bit of a cryptic challenge, and granite's in a way as a sort of melting pot of all the crustal processes, from partial melting to assimilation, crystallization to remelting, to magma ascent, to emplacement, to the overloads that they give, to the high heat production that they may produce or may not produce, to the beautiful landscapes that they form. Why wouldn't you love a granite? That's all I'll say. I can also blame a former teacher on Dingle Academy for being really enthusiastic about it. Now, when we turn to Scotland, we are host, as I said, to about 100 or so bodies of granite, a couple of kilometres square of surface exposure or more, that date to a period of about 450 to about 385 million years ago. The so-called Caledonian and Acadian suites, there are various names that have been applied from over time. But we actually, to be brutally honest, we do not have a defensible plate tectonic model for why they exist. There are many ideas, but there are holes to be picked in every single model. You'll probably pick holes in mine. And not only that, we do make use of our granite bodies. Some produce a lot of radiogenic heat, and we are exploring them. BGS and Edinburgh and Laurentian University, they're exploring eastern corridors for geothermal energy, and this has been going on for some time. Glensanda Superquarry, one of the major employers on the Northern Peninsula, is straight into one of the largest granite bodies of Caledonian age, the Laurentian Pluton. And to be honest, having been there, it is the most fractured, rotten, and horrible piece of rock ever encountered. It's not particularly nice, and the aggregate is helping the Netherlands fight against sea level change. I wouldn't use it very much for any decorative purposes. And at the time many of these granites were being emplaced, there were periods of faulting, thrusting, slip tectonics, the development of our major structures like the Great Glen Fault. Many of these go hand in hand with magmatic emplacement. And now, with the push for net zero, we are drilling into these rocks, the damaged zones of these faults, particularly for things like pump storage hydro. But we have to understand what it is we are drilling into. And it's been hammered home to me recently that an engineering geologist stood in the field where core is coming out from the drilling operation has not got British Standards Institute recipe to follow to describe faulted rock, or indeed to describe, well, this. And we don't really know what the engineering properties of those clay-rich rocks with chunks of granite and bits of calcite and barite running through them. Their engineering properties are a bit of a mystery. And we are putting, for example, the Corrie Glass pumped storage hydro scheme, we are going to be putting £1 billion of energy infrastructure through these rocks. We better understand them. That perhaps is enough of the politics of the game. But our granitoid emplacement events span a couple of these major orogenic mountain building activities that the British Isles have experienced, as said, from about Silurian through to the Devonian. We call these the Caledonian or Scandian orogeny and the Acadian orogeny. Now, over the years, we have all heard about these events, and they have left visible metamorphic, structural, magmatic features on the different terrains. But connecting magmatism to these features has been a problem. Why is there a granite body here or there? Why is there a line of buried plutons here that runs all the way through from Weardale to Leinster? Why is there not a linear pattern somewhere else? How do the granites evolve in space, in time, in chemistry, in what they look like, or in heat production? We sort of know answers to that, but do we really? Just for the definition, so everybody is absolutely clear about what I'm talking about. This is probably the latest definition of what we mean by some of these geological events. The Caledonian and Scandian probably now can be used relatively interchangeably, and ultimately relate to events occurring from the Ordovician-Silurian boundary through to the mid-Devonian, through to the early Devonian, and ultimately, in the UK anyway, result from a collision of the Leinster and Lake District terrain with the rest of Scotland. In the past, the influence of Baltica, Scandinavia, modern-day Scandinavia, has been considered a lot more important, and there is a debate to be had about that. I'm kind of using modern immediate orthodoxy here. The Acadian relates to the subsequent collision of the rest of England and Wales with this terrain collage. Okay? This is a little bit younger, ranging from about 405 down to about 375, 385 million years ago. And we'll come back to some of these as we look at the granite record that may complement these timings.
Oops, sorry, I had the mouse in the wrong place. I was just moving that little pointer out of the way.
Can I do the COVID era next slide, please?
I'll do next. If you say next slide, I'll do it for you.
Perfect. So to give a little bit of a historic perspective about linking granite bodies in some way to plate tectonics. Here's a little snippet of the McCulloch map of 1836 in Scotland. And to show you how far we've come in a way and how far we haven't come, we'll start with this. Helmsdale, Brogart, Migdale and Fern on the seaboard of the Inner Firth. Granites here that are mapped, maybe not accurately located necessarily. There's no internal variation, there's no distinction between what is one type of granite or another, a pink granite, a grey granite, a granite that has biotite in it, a granite with hornblende in it. Simple map. But over time, many of the granite bodies in Scotland and the wider British Isles were ultimately associated with the Silurian and Devonian periods and with what became known as Caledonian mountain building episode. On we go. If we fast forward about 120 years, we arrive at a time when a term that we still use today came into being, and that is the newer granites. And this is where the first of our problems begin. So H.H. Reid, who in his time was quite famous for arguing that many granites were the result of essentially a metamorphic transformation of crust. He had a definition of newer and last granites. And what he really meant was the newer granites were bodies that he assumed, bodies of magma forcefully placed into their country rocks. And you might compare that with the so-called last granites, which were more akin to modern-day caldera forming processes. Granite bodies such as might be exposed in Glencoe, for example, where we talk about things that have connections to the surface, to volcanic systems. So shallow emplacement versus deeper emplacement for the newer granites. But at the time, and going back to one of his presidential addresses back in the early 60s, he certainly recognised that the granites were not just simple granites. They really did involve a wide range of things that traditionally are not what we call granite. Roughly even amounts of quartz, alkali feldspar, and orthoclase, and perhaps some form of mafic mineral. A much wider range of things that are not traditionally granites, but might be referred to as granitoids. But at this time, we had no accurate geochronology to really understand anything beyond their spatial relations. And his attempt at that time was to make this division of newer and last granites. However, in subsequent years, the term newer granites has been basically adopted for pretty much every Silurian to Devonian intrusion that you can see that cross-cuts regional metamorphic features. So these are things that post-date metamorphic activity, major fold structures. That's not entirely true. And as you've said, nor are these bodies necessarily granites. So they're neither new nor necessarily granite. So we should kill that phrase. I love the phrase Caledonian intrusions. It's very, very simple. It is what it is. You've got a gabbro here that's the same age. It's still a Caledonian intrusion. Okay. So we move forward another 25, 30 years. One of my old lecturers here at Stevens. So Halliday, Stevens, many others, ultimately got into the geochemical record of these granites. We have to be aware now that we are into the plate tectonic era. But accurate geochronology is still not fully developed. It's still slow, it's still expensive, with high uncertainties. We don't really know the temporal association of these granites. But what we do know is that there are some spatial designations that can be made with the advent of whole rock geochemistry, mineral chemistry, and some amounts of radiogenic isotope data. And the granites were ultimately split into several suites. Southern upland suite that might nowadays be referred to as a trans-suture suite that goes on across into the Lake District, Cairngorm suite, and then an Argyll and Northern Highlands suite. And finally, although it's not even on this map, a small number of plutons in the very far northwest Highlands associated with the Moyne Thrust Zone that are called really alkaline suites. They're rather chemically odd bunch of rocks, very, very far away from the suture zone that may ultimately represent subduction zone, that may ultimately have helped drive some of this magmatism. And at the time, there was some really lively debate. Researchers such as Matthew Thirlwall in the 1980s spent a lot of time arguing that the chemistry of many of these Caledonian, whether it's intrusions or the associated lavas that can be found in the Midland Valley of Scotland and parts of the southern uplands, made the argument that they were all in some way subduction related. When you think of a traditional subduction zone, a continental arc, that everything was related to the downgrade slab, dewatering, mantle melting, existing lower crustal melting, there's melts arising, fractionating, chewing up crust as they go, and eventually being in place where structural conditions allow. On the other hand, Halliday and Stevens took the view here, there is no clear evidence for a subduction association. In short, they recognised that plate collisions that made this collage of terrains had finished. Yet, there was still magmatism without the subduction zone to form them. We have no cause. What can we do about it? Okay. You notice the large timescales here. Another 20 years.
Something was about something really important.
And researchers were really looking.
I don't think it'll be underneath the like it was the last one.
Can at least see under the bed.
I'll try and kill them all, but I have to.
Thank you. Researchers who were ultimately trying to find a cause for Plutonism in the northwest part of Ireland took on board a model that had been developed by researchers who themselves were looking at magmatism in the Alps. A model called slab break-off. So the idea that once subduction finishes, eventually thinking slab of oceanic lithosphere have to go somewhere. And the thought was, at the time, that eventually just carry on its merry way, 45 degrees, happy as Larry, off it goes, and eventually it breaks, thins and detaches from the overriding lithosphere, and off it goes. And the effect of this would be magma, not magma, but mantle, a asthenosphere, convecting asthenosphere would rise up into the gap, if you like, that is left behind, would introduce heat. Remaining volatiles in here would assist as well with the partial melting of this little tiny block of lithospheric mantle beneath the collision zone. And that would drive magmatism. However, there are some problems here. Anybody who models or even does geophysics on regions where slab break-offs has happened will tell you that slabs do not wander off at 45 degrees into the mantle. They roll back until they are vertical, and then they will sink. Now, a further problem with this is that the magmatic effects of slab break-off are essentially limited to where the slab has broken off and detached. This is where the upwelling asthenosphere, hot asthenosphere, it's 1400 degrees Celsius, will interact with the remnants of this wet mantle, with the leading edge of the downgoing plate as well, which may be felsic, continental crust, easy to melt. But magmatism will be restricted to just those few tens, maybe up to 100 kilometre width next to the suture. Well, slab break-off has been associated with pretty much every neogranite that's had writing done in the last 25 years. It has really been copycatted to be assumed to be the trigger for magmatism across Scotland. Okay, we're talking places that are 300 kilometres from the suture zone. This is far too far away for this to be relevant. Now, of course, I come stealing in here, having looked at volcanoes in Armenia, Turkey, Iran, where slab break-off has also been implemented or implied to be part of the trigger of magmatism. I worked on all sorts of ideas for different models that might be better than slab break-off. Because in countries like Iran, 300 kilometres is nothing. The collision zone between the Arabian and the Eurasian plates is 600 kilometres wide. And still there is magmatism 600 kilometres away from the suture. So we might have some better ideas, we hope. Or maybe just some global ideas that can be brought back home and looked at critically. Okay. To make a bit of a groan, I apologise to Shetland. We're out to Shetland, I'm very sorry. We'll get into trouble with this. The argument that I would make is that, unlike many countries around the world where teams, often of international researchers, have approached places with incredibly systematic geological surveys, Scotland is quite odd in being somewhere that we traditionally think of as a home of geological science. And yet there are glaring data gaps in things that are kind of obvious to do if you have the money. Every Pluton should have a wonderfully accurate and precise date. It should have its geochemical character properly outlined. Well, this is the situation just now. In green, are the plutons that I would consider to have a reasonable whole rock geochemistry, some mineral chemistry data, a reasonable record. They've been studied by multiple people. Recent peer-reviewed papers have come out about them. We hope we know what we're on about. So somebody said, where did this pluton come from? What components melted to help form it? How did it evolve and when was it placed? There's an awful lot of red and orange on this map. It's not good. Carry on. Let's make it worse. I don't want to get into the detail, but this appeared in the 5th edition of the Geology of Scotland volume. It was out last year. And it's a record of dated plutonic bodies, complexes, batholiths even, across Scotland, presenting a range of different methods for producing what we hope to be an emplacement age. And we can see in some places, when we look up the Northern Highlands terrain, you can see some bodies have been dated to reasonable precision. What's reasonable for a rock that is 425 million years old? Well, plus or minus 1 million years is okay. 20 years ago, we can produce a single zircon crystal. It can be dated in Nottingham and the British Geological Survey with a precision plus or minus 250,000 years. Probably we don't need that level of precision, but maybe we're going to get it anyway. You compare this record to some of the Cairngorm granites here, which have plus or minus errors of maybe 7 or 8 million years. And these are purely analytical errors to do with the way that these samples have been processed and run through different mass spectrometry techniques using different radiogenic decay schemes. One thing, however, that is immediately, maybe not so immediately obvious from this diagram, but that the Northern Highlands terrain, the most northerly granites, are the oldest, or amongst the oldest. That granites of the Grampian terrain seem to span a huge range of ages, from 430, which is firmly within the Scandian orogenic event, down to below 400, which is firmly in the middle of the Acadian event. And if we look to the Midland Valley, where there are fewer bodies exposed, many volcanic rocks as well to look at, a sort of narrow range of late to post-Scandian. Southern uplands tend to verge towards younger bodies, in particular ones that are firmly Acadian in age. So there are some trends here, but there are an awful lot of very broad analytical errors. Okay. Let's make it worse. So by early 2023, for the Northern Highlands terrain, which is what I kind of want to zoom in on a fair bit, there are 25 or so Caledonian to Acadian bodies, granitoids in various descriptions. At that point, 24% of them did not have any peer-reviewed uranium-lead zircon dating. For the uninitiated, uranium-lead zircon dating is one of the current gold standards for geochronology. The highest precision, the most detail that you can obtain from these zircon crystals are your friend. Just 4 bodies have been dated to the highest precision methods available to us. And to bring back to the geochemistry, the majority do not have any high-quality gold rock geochemistry. Some bodies like Strontian, Rattigan, and actually Clooney to some extent have been researched multiple times. There are many broad geochemical data sets associated with them. You ask me what weight percent silica does the Ferron granite have, can't tell you. Not one geochemical analysis in the published literature. Oh dear. So how do we establish patterns in space and time when we really have very little to work on? And then the wider issue, this sounds like a moon. It is, sorry. Here is your stereotypical view of a modern continental arc system. We have various concepts about how continental arcs operate on a global level that haven't really been looked at in the Scottish context, particularly until recently. Slab dynamics. Subducting slabs do not enter the mantle at 45 degrees and remain at 45 degrees until they eventually break off. they roll back at different rates. They steepen up. They go shallower. That has a knock-on implication for the stress state of crust that overrides them. Is the crust being pushed and squeezed? Is it difficult for magma to get through that crust? Is the crust being extended and back-arc basins opening and magma finding it easy and quick to get through the crust? The very lithosphere that makes up the continents that we walk on is not stable. It is not of constant thickness over time. It thickens and thins. Blocks of lithosphere may break off with effects allowing upwelling asthenosphere to trigger melting. We've never discussed that in Scotland. But every modern collision zone has this kind of record, and geophysics demonstrates where pieces of lithosphere are ripping off, where it can be correlated to magmatic events at the surface. Well, we don't have the geophysical record, but we do have the magmatic record to work with. And also, what is an emplacement age? It's the final time that a granite body became a granite body. When the rocks cooled and crystallized through the closure temperature of these radiogenic decay schemes, that is the end of the process. How long did it take the magma to rise up through the crust? Did magmas get into the crust and get stuck and then remelt? Did they get stuck and completely solidify and then remelt, or did they get stuck and remain as mushes, a so-called lower crustal hot zone, which is amenable to remobilizing if the stress state is right? If the crust was pulling apart, can they rejuvenate? Global research says this happens. In Scotland, we've tended to focus historically just on the age of emplacement. These zircon crystals, they're resilient little things. They will record multi-million year episodes of growth and storage. What might we find? How long does it take a magma to get from the base of the crust to its final emplacement age, and why does it matter? Okay. Just quickly to put some images on these systems. Continental arcs are pretty long-lived dynamic features. Slab dip, collision dynamics, they change. A very thick crust on an arc of 40 kilometers is considered to be thick. If the crust is being compressed, magma will find it very difficult to rise through. And there is a knock-on effect. The minerals world has worked this out. Magmas will tend to stall in the crust. Relatively few magmas will make it up to the final emplacement depth that we maybe see them at today. Arc systems where the slab is rolling back rapidly, where there is crustal extension, behave a little bit differently. In places where the crust is very thin, these are times when, with the crust being pulled apart, magma just simply rises up very, very quickly to the surface. Probably over tens of hundreds of thousands of years. That is quick in geological terms. Where there's thicker crust, but extension going on, it is quite plausible that new magmas rising up from the mantle will shortcut their way past these lower crustal hot zones, these places where magmas have been stuck under compression. Some will shortcut, some will pass through, some will heat up and rejuvenate these bodies. And your granite at the surface is going to be a mix of all of these things. So transcrustal magmatic systems is the new phrase. Okay. As I said, I'll spend 10 seconds on the slide. Slab breakup is not a good explanation for magmatism when you've got 300 kilometers wide of collision zone from the purported suture here in the Southern Uplands, Northern England. 300 kilometers up to Rattigan up there, and it's been invoked to be related to slab breakoff. Most modern studies of modern arcs really don't point to this being a possibility. And next. As I said, the upper plate may not be stable during collision. Various models here, I want to point you to this simple diagram of what we call delamination. The inherent way that continental arcs operate is that you are adding fluids from a subducting slab. These fluids essentially weaken the lithosphere with which they interact. It can become unstable. In places where the rock type eclogite forms, eclogite is an incredibly dense rock type, the lithosphere again, is prone breaking or dripping or peeling away from the overriding plate. And as a result, we can thin it, we can invoke more magmatism. This is a model that I was a little bit involved with about 10 years ago. We can see here these little regions that mark as depletion, but what they really are marking are little convective downdrafts of the lithosphere. And what we were testing in this scenario is adding more and more and more and more water into the upper part of the mantle will result in the lowermost part of the continental lithosphere becoming more and more unstable, and more little drips of lithosphere will come down. And every time the lithosphere loses some thickness, loses some material, hot asthenosphere will replace that material and heat things up and invoke partial melting. This is probably quite good for Iran. 600 kilometers from the suture zone, if the mantle is still wet enough, this may trigger melting without any other plate tectonic cause. But never proposed for Scotland. Okay. And one final challenge. You may have heard recently from Tony Crave about the evolution of the Great Glen Fault Zone. And it comes back to one of the early things that I said. Is it fair to look at Scotland and say, here are 100 plutons, and they all must be related in space and time in some way to each other? Is it fair to say that when we know that over millions of years, when these events were happening, Scotland was not the body you see today? It was spread as terrains separated by strike-slip faults. If you assume that, for example, the Great Glen Fault had moved 1,000 kilometres, then the Northern Highlands would be sat next to Baltica. These two plates and their interactions through subduction of the Iactus Ocean, that would drive magmatism. But if you only have a small amount of motion on the Great Glen, the 200 kilometres or so proposed by Tony Crave, then ultimately the Northern Highlands, the Grampian Highlands, the Midland Valley, the Southern Uplands are just little jigsaw pieces that are close to each other. And ultimately, the magmas that form are all related, as I said, to collision of the Leinster and Lake District terrain and collision of Avalonia with the Laurentian margin. I will favour that option, perhaps for simplicity here. Okay. Got an interest in doing something about this. I didn't really start out with very much funding, to be perfectly honest, so my initial goal was to set some students up, some master's students, some undergraduate students, to try and assess the validity of some of these emplacement gauges, and where possible, get into the lab. We have a laser ablation mass spectrometer in Glasgow that was installed in about 2016, 2017, and start dating things that haven't been dated. And ask these questions. Is all this magmatism post-dating subduction, or is it overlapping? Do these lower crustal hot zones, these storage chambers related to compression, do they exist, or did they exist? Is there anything temporal that changes with Pluton petrology, with where granites that have lots of uranium, thorium, and potassium that generate lots of radiogenic heat, geothermal targets? When and why did they occur? And I, through out of a pure love for the Northern Highlands, focused there first, but almost by accident ended up looking at the Southern Uplands as well. And these are the granite bodies that I now have, with help, very much help, from my master's students. We have dates for, we have new dates for. We're doing all right. Give me £1 million, I'll be some more. Okay. Here's some of the people involved. PhD student Simon Bright working in Leicester. Tackling Furry's granite that's been recovered from exploration wells in Mary Firth. Foyer's granite, working with me on Strengthian, and he is also investigating. We did a little test for Tony Gray, investigating the granites of northwest Ireland, which may or may not be the other side of the Great Glen Fault. And I suspect that's a point of debate to Tony for some future time. Iain Neill was my first master's by research student. We worked on the Clooney Pluton, but also the Little Glen Loy Pluton near Fort William. Chloe Gemmell and Kieran Cray. Chloe working in the Southern Uplands, Kieran working on more of the granites along the Great Glen Fault. It's been wonderful seeing some of these folk progress. Chlorine Keeling are PhD students now. Ailey, for her sins, has ended up in Dingwall, my hometown, working now as an ecologist. There you go, granites will do that to you. The key point here is that we've got a team of folk who've been bit by bit tackling some of these problems. So let's see what we found. Here's for the Northern Highlands, the improved emplacement record. On the left-hand side is what we had before, albeit with strontium covered up, because we think we have improved on some of the dates, and we've kind of republished some ancient stuff that is now proving very relevant. The short answer is that from purely calculated emplacement ages, very few granites predate continental collision. Very few seem on first glance to predate when two continents collided and when subduction ended. So was there a continental arc in the Northern Highlands or related to the Northern Highlands? Not at face value, just on these emplacement ages. But something else we really uncovered is just how narrow this age range is. Between 400 and 500 square kilometres worth, up to about half of granite, exposed granite, were replaced in just 3 million years. Pretty amazing. But also that if we trust the data, there's a suite of younger bodies, parts of the strontium granite, not all of it, Brechin, Fern, Helmsdale, and so on, that are markedly younger, a few million years younger, but they don't seem to belong to this last of magmatism that lasts for just 3 million years. Critically, you can criticise uranium lead data all you like. There are major petrogenetic differences between, or petrological differences between these suites of granites as well. So let's come to a little bit more. How do these emplacement ages vary in space? Well, earliest granites, of which there are 2 or 3, are very spatially restricted, and most of them are very close to the Great Glen Fault system. Prior to this big upsurge in magmatism, we have the Northwest Highlands alkaline suite, about 430 million years ago, and we have a couple of other bodies, Cluny and Clunes, which is down here, associated either with Scandian thrust, so the Moyne thrust zone, or the Great Glen Fault. Our major burst of magmatic activity is absolutely everywhere. From the Ross of Mull to Rogart and so on, we're talking distances, 50, 60 kilometres from the Great Glen, quite far from a major strike-slip fault structure at the time. No real pattern where they occur, although many of them actually are associated in some way with Scandian structures, folds, faults, etc. But after that time, the younger plutons are entirely close to, right next to, or even cut by Great Glen Fault and its environs. They are very close to major centres of active strike-slip faulting during the Caledonian. So the debate to be had, is the Helmsdale Fault entirely Jurassic, or is it a reactivated earlier structure? It's Caledonian, don't know. But there is some spatial pattern here. Next one. Not the best at showing pictures for this, and I apologise, I flew before Christmas and would have done a better job if I wasn't cupping my guts up. But there are petrological differences between these suites of granites. Some of these time patterns have kind of a muddle of rocks. The earliest bodies range from just boring granite, like the one shown here. This is the linear or Ardgour granite, 440 million years old, through to mafic, even ultramafic bodies of industrial cyanite and some of its associated mafic bodies. Like a good example, we're all this thing at about 450 or so million years old. You move to the time of the Moyne thrust, about 430 million years ago, you get this burst of 2 different types of magmatism. Some highly alkaline, odd rocks with weird names up in the Northern Highlands, and then you get these incredibly boring, plagioclase-rich granites that Cluny and Clunes that have their own stories. I think I have a reasonable explanation for why they exist, but we'll come to that. But this variety is then replaced with this middle burst of magmatism, and until you know the ages, you don't realise it is a middle burst of magmatism. But now we do. We realise that they're all the damn same. they have a very odd high barium, strontium, and other light element enrichment. When you look at a thin section of them, they almost ubiquitously contain amphibole and titanite, calcium titanium silicate. They are not really granites. They're slightly less evolved than that. They are mostly granodiorites. Here from the strontium granite, almost all of them contain mafic enclaves, evidence of contemporary mantle-derived magmatism, blobs of mafic magma that arrive in plutons that are segregated and broken up and mingled with the surrounding magma. They're all there, they're present. Often there are mafic facies, not just granodiorites, so there are diorites, gabbros, and so on. And when we looked at the zircons, like I said, zircon, the tough little buddy, these bodies contain lots of zircon that grew at the time of emplacement or shortly before. Very little what we call crustal inheritance. Zircons that come from chewing up of the crust as the magmas rise up. So there's no Archean zircons in these, or very few, or fewer Archean zircons. There are fewer Proterozoic zircons. The inference being these granite or granodiorite magmas have risen up pretty quickly through the crust without the time to swallow it up on the way. Compare and contrast, the latest granites are the dullest things imaginable. They're pink, ubiquitously pink, almost no mafic minerals in them, and the zircons, well, some of them I've really struggled to get an age out of because most of all the zircons are inherited. These are crustal melts. These are not mantle-derived magmas that rise up, chew up a little bit of crust and fractionate and grow pretty quickly. These are crustal melts. Something thermally has disturbed the crust, or something else has happened in the crust to trigger this. We wouldn't have had this association if we didn't have the dates to know that these were separated by time as well as time. Okay. The other point about zircon data, and this is just one example from Clooney, that we discovered this back in about 2019, and it was a bit slow in getting published, but we got, is that the age at which the body was emplaced is not the only story that's preserved in these zircons. Indeed, probably a slim majority of the granites of the Northern Highlands, there are a range of zircon crystals that appear to be crystallizing some millions of years before the granite was in place. Now, in modern systems, modern arc systems, we talk about something called anticrysts. Anticrysts belong to the same magmatic system. Imagine a magma rising up into the lower crust. It starts to crystallize, it generates some crystals, including zircon, and it maybe sits around for a while. Now that zircon can record an old state that may predate that magma eventually rejuvenating and rising up into the higher parts of the crust and finally being placed. I suspect, given that these are 10 to 20 million years older than the age of emplacement, I suspect that may not be necessarily true. These are maybe xenocrysts, just ones that are 10, 20, 30 million years older than the age of emplacement. In other words, they are evidence that magmatic activity was occurring in the Northern Highlands back to about 450. Just that none of the magmas made it up to the emplacement depth you see like today until much later. And we've seen this across much of the Northern Highlands. Myself and Chloe Emmel from the Southern Uplands discovered the same thing with slightly different timing in the Southern Uplands, and Donnelly Archibald and colleagues working in the Donegal area in Ireland recognised the same thing in Grampian terrain. This pre-emplacement zircon growth is evidence that there was an active magmatic system at the time before the plates all collided. In other words, there was a continental arc. But it was a continental arc that had to be under compression, so that the magmas never had a chance, or very rarely had a chance, to make it up to the final emplacement depth. And only when the subduction process was finishing, and the slab was rolling back and the crust started to extend, could these magmas start to infiltrate the crust again, be rejuvenated, and rise up to their replacement depth. So this is pretty cool. I really liked this story. I suspected it for a long time. It was beautiful to see something like this eventually emerge. Okay. So let's wrap up the geological story, sidetrack. What do we know so far? What can we do so far with this in terms of the plate tectonic model? Now, I apologise for the sort of randomness and relative thickness of the lithosphere here and various things. We're talking something in this time slice about 400 kilometres or so across, 350 kilometres or so across, from the southern uplands and the Solway line, the Aptus suture in the far right of the diagram, up to the Northwest Highlands and the Moyne thrust here on the left-hand side. So initially, in the top diagram, arguments have been made to basically extend the Caledonian orogeny back to about 450 million years ago. Metamorphic researchers are realising that at that time there is evidence of quite high-grade metamorphism. It used to be called Grampian 2. We now think it's just the start of the Caledonian or Scandian. That's about 450. So the crust is thought to have been being compressed at that time in the Northern Highlands. Well, this is the time when my zircons start growing. So this is the time when, for some reason, the crust is being compressed. Is it some form of collision? Is it an early onset of continental collision? Or Tom Lamont, who used to be working in the UK, in North America, somewhere now at the moment, he proposed that there was an episode of what we call flat slab subduction. And this is quite tempting. It comes with many of its own problems. But flat slab scenarios, there is one today beneath modern-day Colombia, for example, result in compression of the overriding plate. So this might be quite a nice way. Subduction dynamics leading to compression of the overriding plate, leading to a reduction in emplacement of magmas way up at the top of the crust here. But they ultimately are magmatism would be stored in the lower crust. But also, notice where eventually the slab gets deep enough to dewater. To make magma, you need the water coming off the slab. Well, you can't do that where there is no mantle wedge to put this water into. So it's not happening beneath the southern part of the Grampian Highlands or beneath the Midland Valley. No magmatism, or very little magmatism. But it is active beneath the Northern Highlands and the northern part of the Grampians, where we've identified this pre-emplacement zircon growth. When plates start to collide, when the Lake District, Leinster start to arrive at the Aptus suture, this triggers the Aptus slab to start to steepen and roll back, eventually in the run-up to breaking off. So by about 430, we have a broader region that we would call traditionally a mantle wedge. And the dewatering of the Aptus slab is triggering melting, the crust is beginning to relax and stretch apart, and magma is able to start rising up and becoming the granite plutons that we see today. Accessing the Moyne thrust, the Northwest Highlands alkaline suite, the early granites like Cluny in the Northern Highlands, and like Aldern in the northern part of the Grampian Highlands. All is good. Just a reminder at this point, the plates here are still colliding. Subduction is just about to end, but things are still being compressed. Follow that on to the next slide. 44, the middle of our peak of everything happening at once. So here's southern uplands. Should be a mantle lithosphere attached to this, my apologies. Slab breaks off. But the effect of slab break-off is that in the southern uplands, magma can start to rise up into the former accretionary complex. Because the slab is now absent, it essentially rises up. The lower crust, the downgoing part of the northern edge of the Lake District starts to get burnt, if you like. Magmatism begins. We'll come back to that. There's no emplacement at this time into the upper crust. All the magmas are still stuck in the lower crust. But towards Grampian Highlands and the Northern Highlands, all hell breaks loose. This is our peak of magmatic output. And it can't really relate to the slab break-off hundreds of kilometres away. Well, the rollback of the active slab The wetting of this lithosphere by the subduction-related fluids has led to an inherently weak lithosphere. Now, with rising convecting asthenosphere, this is breaking off. Maybe piecemeal, maybe entire chunks, maybe peeling away, but delamination, we call it, the removal of this weakened hydrated lithosphere. As some of the delaminated lithosphere sinks, it can begin to melt, particularly if it is hydrated. The asthenosphere rises around these delaminated chunks and triggers melting. And overall, the addition of magma to the lower crust heats up that lower crust that has all these old stored magma bodies. They all rejuvenate and we get our huge volume of plutonic rock. As I pointed out in the previous slide, just because subduction has apparently finished doesn't mean that plates aren't still colliding. And maybe an argument people might say is, but yeah, 424 is the peak of Scandian orogenesis. This is where the Northern Highlands have these huge upright, kilometre-scale upright folds in them. So if the plates are still being pushed together and still colliding, then surely you've still got subduction or something like that. Well, let me point to places like Turkey, Armenia, Iran. These are places where the slab disappeared 5-10 million years ago, but the plates are still colliding at several centimetres per year. There is still a major fold and thrust belt between Iran and Saudi Arabia, and there is a complementary one on the northern side, the Greater Caucasus Mountains, and the South Caucasus, and various other mountains, the Alborz of Iran. These plates are still coming together, orogenic activity is still happening, but the lithosphere is much thinner, hotter, and magma is getting up through it. Okay? This is an odd thing to think about. The crust is somehow being simultaneously squeezed, but also magma can get through it. What's the other recipe here? Strike slip faulting. Okay. Peak time for movement on the Great Glen Fault and other associated structures. There are structural gaps. There are structural places where magma finds it easier to make it through the crust than others. And many researchers, going back 30 years or more, actually more 40 plus years, pointed out the strong association between granites being placed and the proximity to major thrust faults, to strike slip faults, to underlying lineaments and discontinuities in the older basement rocks beneath. So I don't think there's anything wrong here, majorly wrong. Somebody wants to poke a hole in it, they're welcome. Okay. And at the end, the Scandian is done. When does it all finish? About 418, 417, 416 is traditionally the time that the strike slip faults move from transpressional, transtensional. The crust is starting to relax. Uplift occurs. Shortly after this, we'll get the old red sandstone deposited. What does uplift do? It decompresses the crust. This is hot crust that has had a lot of magma passing through it. This is prime opportunity for decompression-related crustal melting. Kind of thing that happens in Himalayas. Okay? The last melts in the Northern Highlands, as I said, are these granite bodies, entirely crustal melts. No mafic enclave, no evidence of mantle-drive magmatism. These are crustal melts. So the uplift and decompression, when the orogenic activity finally wanes, I think gives us our answer to why the last of these granites are imposed on the Northern Highlands. Okay. I like it. I didn't stop there, unfortunately. Now, I'll race through some of these just to quickly point out. We did the same thing in the southern uplands, and we found this pre-emplacement zircon record is pretty true there as well. And basically, magma got into the crust after about 46, 45, 44 million years. Well, the southern uplands, as we all appreciate, is some kind of accretionary complex in front of this mountain belt. The accretionary complex is not where arc magmas form. It's far too close to the suture. There should be not enough heat to form magma. The only way you can get magmatism in this is if the slab is rolled back and potentially broken off. So here's our timing of slab break-off. 46, 45, 44, something around that time. Magma, you see in orange here, starts to get into the crust. But in grey are our final emplacement ages and errors. This is distance, by the way, so the sort of thickness along strike of these bodies. But the key thing is magma starts to get into the crust, and then the overall orogenic activity wanes, crust starts to extend more, we move to transtension, and you have all these emplacement events from about 416 onwards. That was a problem. The way I've described slab break-off in particular talks about magmatic activity occurring pretty much at the suture or within 100 kilometres maybe to the continent side of it. Leinster and the Lake District have got batholithic proportions of magmatic emplacement south of the Iain suture, quite some way south of it. How do you explain that with slab break-off? Okay. So many of these granite bodies actually carry on being in place well into what we call the Acadian orogenic event. Now, the Acadian is better known to people working more often in the Lake District and so on. There is evidence of metamorphism at this time, structural events. But let me just tell you, the Great Glen Fault was active during the Acadian. Sinistral, strout-slip faulting, and very rapid uplift actually along that structure. So the Acadian had quite far-field effects, but what was it? Well, I described it as the collision of the English Midlands, Welsh Midlands with the Leinster basement terrain here. So, what if a better explanation for these granites is nothing to do with the Iapetus suture, but a final tract of the Iapetus ocean that may have existed between the Leinster and Lake District terrain and the Midlands of England? Because nobody in the past had talked about where the Acadian erosion came from. They just said crustal blocks colliding. But to have collisions, you presumably have to drive collision with some form of tectonic activity, like subduction. What if there is a tract of oceanic lithosphere that once existed between these regions? Well, at pretty much the same time as I was sat at the kitchen table over Christmas about a year and a bit ago, thinking about this and sending frantic messages to my master's student going, hang on, I think we've got something here. John Waldron, professor over in Edmonton, started to propose something called the Inishmoth, or Anglesey line. He based this line on a gap in the sedimentary record, the Welsh Basin. Now, I'm not going to get into justifying John's approaches, but his argument essentially ended with potential evidence for a structure that goes between the Welsh and English Midlands and Northern England. Some seismic evidence offshore in the Irish Sea. Very little else that's been talked about because we don't have in geophysics. But evidence of a small tract of the Iapetus Ocean that existed between these blocks that closed, and when collision occurred, that caused the Acadian erosion. And I immediately thought, what's the timing of this? Well, it's about 400 and something. Okay. Well, how do we do it then? Here's our linear chain of plutons, about 80, 90, 100 kilometres north of the Inishmoth line. So, at 426, our Iapetus slab has done its job, it's broken off. Still, the northern edge of the Lake District is trying to push down, trying to subduct, but it's done now. So what happens to subduction? You've still got some Iapetus ocean to close, it backsteps. Subduction commences at the Inishmoth line beneath the Leinster and Lake District terrain and produces a short burst of granite magmatism. That slab will roll back when the English and Welsh Midlands arrive. It will roll back and eventually break off, just like the Iapetus slab would have rolled back and broken off, but 30 million years later. And here, potentially, another subduction zone, another rollback and extension, another break-off, another destabilization of the lithosphere. This, potentially, is why, from the Grampian Highlands all the way south, you have this ongoing magmatic record that completely postdates Caledonian erosion. I like it, but we need to prove it. Led by a geophysicist in Edinburgh, there is now a move to do a passive seismic survey of the UK and first proper onshore geophysical survey of the whole UK for over 40, 45 years. And we'd like to ground truth some of these sutures. from Iapetus to the Inishmorn line to various other crustal discontinuities. If this happens, this is our ultimate test. Is there suture zone there that haven't been recognised? Okay, carry on. Wrap this up. We're political. So this is our final model. We need some revision. I should say McCrae et al. In revision. We're letting a master's student here in McCrae is going to lead on the production of this. We've had a good go at it. We've got some moderate revision to do. But hopefully the Scottish Journal will be gaining this revised model of the plate tectonics of the Caledonian and Acadian orogenes. Said some debate over the influence of Baltica, but we're getting there. Okay, we have a model that we think is reasonably defensible, and there are some testable hypotheses we can build from that. Okay. Political interjection. Let's move on. I appreciate I talked for a long time and it's getting late. What can we do with these grants? As I said, some of them are crustal melts. Crustal melts, if you're melting something like a peelite with a mudstone of some form, quite often these are enriched in many of the light elements and uranium, thorium, potassium, things with radiogenic decay going on, heat production. So this last burst of granites, 418 in the Northern Highlands and about 408 in the Grampian Highlands, are the high heat granites. Maybe we should do something with them. Geothermal energy. Could we? So this is my provocation. This is Alness. This is one of the giant wind turbine blades on its route in. The Northern Highlands, in particular, is not an area of the UK that is immune to energy transitions. Electricity for some of the most rural areas came from the building of the hydro dams. We had the oil and gas revolution. We had the yards opening up and closing. We now have the wind energy revolution. Now, every single of these revolutions, if you like, has brought economic, social, and sometimes environmental change to the Highlands of Scotland. But the critical thing is that whether it's political or practical or big company interests or what, none of this is making anybody's electricity bills cheaper yet. And rural communities in the Highlands, semi-rural communities in the Highlands, are seeing masses of energy infrastructure being put up, but it is not benefiting them. There are community benefit funds that are tiny in relation to the money that is involved in the production of green energy. So, on we go. Thermal energy, heat, is not something you can travel very far with. Okay? You lose a few degrees perhaps for every kilometre that you take hot water. As a result, district heating networks are becoming of increasing interest. And let's go on to continental Europe. These are big things. These are important parts of the infrastructure of towns and villages. District heating, based on a geothermal source of energy, deep drilling into the crust to find sources of relatively hot crust, extracting that heat in some form, an open loop system would involve pumping water into deep underground, wondering where it will go, getting that hot water back. A closed loop system is like a ground source heat pump. Take a saline solution, put it into deep pipes underground. In Bavaria right now, reaching 4.5 kilometres, closed loop system is going to power and heat a town the size of Inverness. So we should do it, shouldn't we? One of the main drivers for this is the idea that you could community own your heat production. Now, if you go back to the Highlands before hydro, pretty much every major town settlement had its own electricity company. Well, why don't we have our own geothermal companies for each town? Would this be too far a step? Let's go on. This is the kind of system we're talking about in Germany. Deep drilling, 2, 3, 4 kilometres. And now we're into sub-horizontal drilling, nodes and branches, pipes with high heat transfer potential, filled with saline solution, passively taking the heat up from whatever is underground. And let's imagine for a while the kind of companies that are putting this together, big kind of startup companies. What they're now telling us is basically it doesn't matter what the geology is. If you drill deep enough, it'll be hot down there. Okay, we know what a geothermal gradient is, it's hot down. It would be better if the rock was locally hot for whatever reason. So an aquifer with lots of water flowing through it at great depth, that will transfer heat very readily. Or a high temperature granite where the rock is hotter locally than the surrounding rock, and that would be good as well. And if that were present, then you would need to drill less, drill shallower into the crust to get that heat back to the amount that you require for your community, so we could make it cheaper. Okay. I hope this is not snake oil for anybody. Places where high heat flow may occur, where the crust is thin, the Northwest Highlands, where there are big fault systems that enable heat to transfer more effectively, where, for example, there are sedimentary basins like the Old Red Sandstone here, maybe covering high heat granites, thermally covering them, trapping heat underground. This may make drilling operations more economic. So I'm telling you now the Northern Highlands has some of these characteristics. Just because much of it looks like old coal gneisses and schists and things, it's not Iceland, it's not got active volcanism, it may still be really good for geothermal energy. Okay? And some of the highest heat granites, I said, were very close to the faults. Grampian, Fern, Helmsdale. They're also very close to where the people and the industry and the agriculture are. The Old Red Sandstone, the fertile farming country, the place where the highest populations are on the Inner Firth seaboard, may be covering high heat granite. Maybe. We'll have to find it, if there is any there. But this is looking good. Carry on. Is there a high geothermal gradient? Is there any evidence? Have we got any evidence that there is hot rock at relatively shallow depth? The bad news is we've hardly ever looked. It's quite upsetting. Lothbeck is a borehole that was drilled just offshore near Helmsdale into the Jurassic and some of the Old Red Sandstone rocks that are just offshore. We have the Helmsdale granite, Helmsdale fault, Jurassic normal fault, and then you have the offshore, you have the well right next to it. 40 degrees per kilometre is the recorded geothermal gradient, higher than pretty much anything else recorded in Scotland. Now, many of these are somewhat odd heat measurements. We'll come back to that problem in just a second. But there is evidence that some places at least are hot. Okay. So this is what I was kind of describing with lots of arm waving. Devonian Helmsdale granite. Here's where the borehole was drilled down to about 750 metres, and we're recording things that are hot. Just remember, in the upper crust into these sedimentary rocks, there may still be permeability, there may still be fluid flow, effective ways of getting heat to be removed from these rocks. What if you drilled down into the Helmsdale granite, which is a high heat granite? How hot really is the geothermal gradient? Is it really 40 degrees per kilometre, or is it maybe a bit higher? Either way, how do we know if we're going to go, let's say, the Black Isle? Lots of Old Red Sandstone, a few hundreds of meters of it. Are you going to find a granite if you drill beneath it? Well, one thing you could do is passive seismic survey at a relatively small scale. Set up seismometers in 6 months, a year, and use that to understand the structures beneath your feet. But potentially use low temperature thermochronology. This is a specialist technique involving small crystal of zircon and apatite and measuring. Ultimately, low temperature, moderately low temperature events and when they happen. So little crystals like apatite, we can undergo various measurement techniques that can tell us when they were at temperatures of, let's say, 60, 70, 80 degrees Celsius or so. Now, if you were to raster sample the Old Red Sandstone and work out when it was last at those kind of temperatures, if ever, you would find, I hope, pockets where it did reach those temperatures and pockets where it didn't. Would that be a way of finding where that hot granite underneath that influenced the thermal properties That would be lovely to try. Seismic would be cheaper, to be honest. Okay. So this system at Helmsdale, what could we potentially do, and how does this feel political? Here's our borehole. Yes, I have shown this before. I've done something convenient. I've not put the geothermal wellhead over the local cemetery. My apologies. But a key point about this, Helmsdale, 750 people, 1 square kilometre, perfect for a district heat network. Already the community group that I've spoken to up there have basically said people who put in air source heat pumps are struggling badly. Because many of the homes are not properly insulated. They are not suitable for what are relatively small scale and individualistic approaches to changing from hydrocarbon-based heating. Supplying abundant heat energy from a geothermal system might be the way around this. Now, siting a borehole on community-owned land may be something that is now politically encouraged. If we were to drill, for example, into the Helmsdale Fault, fractured but hot bedrock, circulating hot water in it, this could potentially reach 80, 100 degrees Celsius or so at about 2.5 kilometres. This is a rough guess here. We need to constrain these things, we need to do the on-the-ground work, but we could have a geothermal system that suits somewhere like Helmsdale. Scale it up. What about Inverness? Okay, next. So we do need to do some work. Lots of the past measurements of heat flux through the UK. Look at Cornwall here with its wonderfully high heat flux, really perfectly matched to the position of the granites. That's great. Do you think a map of Scotland looks anything like the geology of Scotland? What on earth is the shape of the cairngorms going across the Loch Ness with the sort of high heat? Why does it look like that? It looks like that because we have a terrible record of drilling holes in the ground and measuring the temperature. We've not got enough data. So we need, ultimately, to obtain thermal properties of the rocks of the Highlands and the rest of Scotland and the rest of the UK, let's face it. And that is happening. Joy Falcone, who heads up our engineering school, is leading an engineering and physical sciences research council grant at the moment, collect rock properties, heat capacity, heat production, thermal conductivity. We then need to invert those data with a seismic model to understand the heat flow through the crust. The Irish have done it 2-3 years ago. We have a perfectly serviceable map of the temperatures at depth in the crust beneath Ireland. Many parts of southwest Scotland have crust very similar to the Northern Irish crust. That is an out-of-date map of the Northern Irish model, I should say. But the key point being, they're predicting within the range of what we can drill to today, there are temperatures of up to 150 degrees Celsius. You could get geothermal heat. You could also drive turbines and generate electricity. Okay. I'm not going to focus on this for anything longer than 10 seconds. We are on a continental margin, a continental shelf, pretty much. The north of Scotland should have high heat flow. Based on bigger mantle-scale geophysical models, Scotland, with this lovely warm pink colour here, should, in the Northern Highlands, have very high heat flow. However, the surface heat that is observed is both rather low, and look at how few measurements there actually are. So there is quite a big differential between predicted and measured. And not only that, there are issues with many of the heat flow measurements. Heat flow around Inverness and the Great Glen was measured by looking at the temperature difference in the sediments at the bottom of Loch Ness. Not exactly the gold standard. Okay? So, we may have really good geothermal potential, but we just don't know it. Okay. Final sort of slide, I think. I apologise for the length of this. Wind farms built, planned, some rejected, some being scoped, some approved in that region that I showed in the McCulloch map, Scotland. This is the future. But the local communities feel powerless to project, to be listened to, this is not their energy future because their bills are not getting cheaper as a result of having this energy infrastructure. Community partners that I've spoken to across the north of Scotland have been really positive about geothermal. Once they understand what it is, people don't know about geothermal energy. Ultimately, they see this idea of locally owned district heating networks as A, better than heat pumps, but B, it's not competing against wind turbines. The energy they're generating is huge. We don't need that much to heat homes in the Highlands. But they appreciate it's a way of getting some economic control back. If they can front up the costs, however it may be fronted up, we have a model here that could work. And this is now being explored in various places. Even the city of Cardiff is now looking at models for how we can get a sort of community-driven heat system put in, however the source of the heat comes. Okay, I've gone to these communities before we have data. So they appreciate that we may not be successful, but they don't mind. They like being spoken to first and explaining what we're doing, and they're really supportive of it. So I'd like us to continue this process of constraining where the geothermal comes from. Having that geological background of understanding the crustal structures, how it came into being, is really fundamental as a starting point to this. Anyway, we're looking at these Caledonian and Acadian events. We now think we maybe have a better understanding, more globalized understanding of how Scotland came together. We've accidentally proposed a new suture in southern Britain, and we've maybe got a bit more flesh on where the high heat cramps are and why, and we're starting to go towards that application stage. Okay. Next slide. Or is it the final slide? Yes, it's the final slide. Right. So I'm very curious, Zircons probably have some questions for me. It's sort of the Rorschach test, okay? But thank you very much for listening. Thank you very much.